Hello dear students, welcome to Pen and Paper Chemistry on YouTube. We have already dealt with redox reactions in the earlier, I think 4 or 5 videos, where we have also spoken about balancing of redox reactions using two different types of methods, the oxidation number method and the half reaction method. Continuing with our concept and with our idea of redox reactions, we are now going to extend it to study what we call as galvanic cell or voltaic cell. I will again pick up from where we had left. You immerse a zinc rod in a solution of copper sulfate. Now this is one simple experiment that the teachers many a times make the students do in the laboratory also, and it is used as a demonstration reaction as well. Now zinc rod is actually silvery white in color, or you can use zinc granules also. Copper sulfate solution on the other hand is blue in color, right? Now when we immerse a zinc rod in a solution of copper sulfate, there are some major changes that you will observe immediately. First, you will see that the zinc rod starts dissolving, it starts becoming smaller, or if you are using zinc granules, you will see that they will start disappearing. The color of the copper sulfate solution starts to fade away. It will become pale in color and then finally slowly it will start disappearing. Mind you, the color of the copper sulfate solution is because of the presence of copper ions in the solution, right, which are there in the aqueous form. What we notice over here is at the bottom of the vessel you will see a flaky appearance. Usually it is reddish brown, but when you are seeing in the solution you will see it as blackish flakes. What are they of? They are of copper, which is getting deposited at the bottom of the vessel. You will also notice bubbles rising, and you will notice that the beaker will become slightly warm. That means this is an exothermic process and heat is being liberated in this process. Now this is a very simple example which can be explained with the help of the redox reaction. What is the reaction that is taking place? Zinc is displacing copper from its compound in aqueous solution. So zinc says, oh, come on Mr. Copper, please move. I'm stronger than you in reacting with sulfate, and it forms zinc sulfate. Copper gets separated out. It doesn't have a companion, it starts settling down. And in the entire process, heat is being liberated. That means it is an exothermic process. This can simply be put as the reaction Zn plus Cu2 positive gives you Zn2 positive plus copper. Why? Because sulfate ions are remaining unchanged as a reactant and a product. In other words, when this reaction is taking place, there is a change. There is a change in energy. So there is chemical energy getting converted into heat energy, right? So that means that energy is getting wasted, right? You are not using it anywhere. Why not try and convert it into some usable form? I don't want it as heat energy. What we can do is we can convert it into a form in which it is usable, it is user worthy. How do we do that? We'll carry out the same reaction, but we will slightly change the setup over here. So what we are going to do is, instead of putting zinc in copper sulfate solution, we will put zinc in zinc sulfate solution. Yes, this is one change that we are going to do. So what is happening over here is zinc metal is in contact with zinc ions. Zn is in contact with zinc ions. Where does the copper disappear? Nowhere, it is still around. What we are going to do is, we will get another beaker. Okay, so let's connect another beaker over here. Wherein, what do we do now? So we have a beaker in which we will take copper sulfate solution, and in this copper sulfate solution, it is aqueous copper sulfate solution, and we will immerse a copper rod in it. Now, immersing a copper rod means, again, copper is in contact with copper ions. So, we've got a copper rod in contact with copper ions over here. What next? Oh, we've got actually separated them, right? So, but according to our redox reaction, they should be in contact with each other so as to be able to carry out the redox reaction, correct? Okay, let me connect them by a conducting wire. Let me do some mischief over here and we connect a bulb over here, right? What do we notice? Oh, the bulb begins to light up and the solution does not go as warm as it was going in the first case. Yes, the solution loses its color here as well. Zinc rod dissolves, absolutely. Color of copper sulfate solution starts fading away, correct. Reddish brown flakes of copper deposit at the bottom of the vessel, yes. Heat is liberated, no. What is happening over here is, we are converting that chemical energy to electrical energy. So what you have done over here is, you have channelized that energy into something which is useful. And that is what we call as a galvanic cell or a voltaic cell. But what do we notice is that this bulb lights up only for a short time. It just stops working. The setup stops working within a short time. Oh, why is it happening? And what is happening in the entire process? I need to understand that. Zinc is in contact with zinc ions. Here, zinc has a tendency to change into zinc ions. It likes to stay as an ion rather than as a metal. On the other hand, copper ions have a tendency to get discharged and turn to copper. It likes to stay as a metal and not as an ion. That is if it is given a choice. Combining the two electrons lost, loss of electrons. Recall what we did in redox reactions, right? Loss of electrons is, yes, oxidation. Copper ions, they gain electrons. Gain of electrons is what? Perfect, it's reduction. So what we are doing over here is, we are utilizing the concept of redox reaction. So if you combine the two reactions, how have I combined the two reactions? By connecting them with each other through this conducting wire. What do we have? Zinc plus Cu2 positive gives Zn2 positive plus copper. Oh, voila, this equation is the same as the first one. Correct? So we are using a redox reaction in order to convert chemical energy to, yes, you are converting it into electrical energy. And this is the very principle of a galvanic cell or a voltaic cell, right? These terms are given after the name of the scientists who worked in this direction. Now, okay, all good so far, but just now we said that this works for a very short time and then stops. Why is it so? Go back to physics, where if you recall, when you operate any device or when you operate any electric gadget, you always have two pins in your point, right? The live wire and the neutral wire, correct? Current enters through one and leaves through the other, so it has to be a closed circuit. My circuit is not closed because zinc is losing electrons, forming zinc ions, and with the result what will happen is there is an accumulation. Yes, there is an accumulation of electrons there's an accumulation of zinc ions over here. We get an excess of zinc ions in the first beaker. What about the second beaker? Yes, we agree that the electrons will start flowing from zinc to copper in order to generate current. But in the process, because copper ions are getting discharged as copper, they are taking up 2 electrons, we will have a buildup of excess of sulfate ions in the solution. Whereas in the first case, when we had directly put zinc rod in a solution of copper sulfate, zinc was simply combining with the sulfate ions and giving us zinc sulfate. So we need to do something, right? Because otherwise this becomes a one-sided arrangement. So what do? We connect the two of them by means of something which is called as the salt bridge. I will draw this diagram again so as to make it more clear, and what is the function of the salt bridge, that also we will discuss. Now if you see, electrons go from here, go from zinc towards the copper. So what is the direction of the current? Again, recall your physics. Correct. Current will flow from copper to zinc. I don't know for whatever reason they have put this conventional current, but that is how it is supposed to be. The electrons, they flow from zinc to copper. The conventional current, we say it flows from copper to zinc. So if I connect a galvanometer over here instead of a small light bulb, now this bulb is not your 100-watt bulb, it's a small bulb. If I connect a galvanometer over here, the galvanometer will show a deflection towards the zinc rod, showing that the current is flowing from copper to zinc, but the electrons are flowing from, perfect, zinc to copper, right? Now let me draw the diagram again and explain to you the functioning of the salt bridge. I think this looks neater now. I've drawn here a galvanic cell or a voltaic cell. Again, you've got a zinc rod dipping in a solution of zinc sulfate, copper rod dipping in a solution of copper sulfate, and the additional thing that I've drawn over here this time is the salt bridge. So salt bridge, that's a salt which serves as a bridge between the two components of this galvanic cell, right? That is very clear from the name itself. It's a bridge made up of a salt solution. So what kind of salt are we going to take over here? So basically salt bridge is a U-shaped glass tube. That's technically it's a glass tube. When we show this experiment in the laboratory, what we do is we sometimes simply use a filter paper dipped in the solution of the electrolyte which we are using in this particular setup, right? What is it made up of? It is either a concentrated solution or a solidified solution. Solidified solution means we make it kind of a paste in agar or gelatin. So concentrated solution or solidified solution. Why are we taking concentrated solution or solidified solution? What if you had a liquid in a glass bottle or a glass tube like this? So you have a liquid over here and you had to invert this glass tube in this beaker, what will happen? Simple, it will flow out immediately and the whole purpose will be lost. So what do we have? It is, we have concentrated solution as a solidified solution. The other advantage of using a concentrated solution is then in that case we have a very high percentage of the salt component, of the solute component. The solute that we are using over here is an inert electrolyte. Now inert doesn't mean that we are using an inert gas over here. It's an inert electrolyte. What do we mean by an inert electrolyte? An electrolyte which itself does not take part in the redox reaction. That means it will be there. It will participate, but it is not a participant in the redox reaction that we are talking about. That is zinc plus Cu2 positive changing to Zn2 positive plus copper. This is the redox reaction we are talking about. The electrolyte that we are going to use in this salt bridge in no way disturbs this redox reaction. And individually also it does not react with any of the solutions. So the salt bridge, the ions of the salt bridge that the salt that we are going to take over here will not react with either the zinc or the sulfate ion or the copper and the sulfate ions in the two parts of this electrochemical cell. Examples of such kind of electrolytes are KCl, KNO3, K2SO4, etc. You can also have NaCl, although potassium salts are preferred. Now, if you notice over here, we are taking salts of compounds which are highly soluble. So what happens is, you do not get precipitation over here. So what will happen is, if you are using a salt over here, we'll understand the functioning, then we will understand what we are talking about precipitation. How does a salt bridge function? What is the role played by a salt bridge? As we said, it acts as a bridge between the two halves of the cell. What are these two halves? So this galvanic cell is made up of two halves, that is the zinc half and the copper half. Right? Now in the zinc half, we notice that zinc is getting converted into zinc ions. Right? In the copper half, we have seen that copper ions are getting discharged and turning to copper. Copper ultimately getting deposited onto the electrode, right over here. Now, because of this, there is an accumulation of zinc ions in the left hand side beaker, whereas in the right hand side, there is an accumulation of sulfate ions. The electrons are happy that okay, we are being released, let's go, la la la, and there they go, correct? They move towards copper. The current on the other hand moves from copper to zinc. Everything is in place. But in the entire process, the two solutions are suffering. In one, it is the positive ions which are getting collected. In the other, it is the negative ions which are getting collected. So what will happen is, over time there will be a build-up of the charges in the two solutions and my whole process will come to a stop. Before this process comes to a stop, we introduce the salt bridge. So let's suppose I am using a salt bridge made up of a solution of potassium chloride. What will the potassium chloride do? We know that potassium chloride is an ionic compound. It breaks down to form potassium ions and chloride ions. Not exactly break down, it is made up of potassium and chloride ions. Now what role is played by the potassium and the chloride ions? As soon as the chloride ions see that there is a buildup of positive charge in the left half of the cell, that is the zinc half of the cell, it starts moving towards zinc. When it moves into the solution, there is zinc ions, there are chloride ions in the solution. So what will happen? That buildup begins to reduce. come to copper sulfate solution. Now here there is a buildup of sulfate ions. Oh my god, potassium sees, okay, this is a situation of distress. So what happens is, through this glass, through this bridge, potassium ions, they move into the copper sulfate in order to neutralize the buildup of the sulfate ions. It is just like an example where you see that in your class there are certain students who are very good in physics, there are certain students who are very good in chemistry, right? So we form a bridge between them. We ask them to help each other out. How? There's a third student who steps in, or there's a third group who steps in, and they help the students who are weak in physics and they help the students who are weak in chemistry. So that way the balance of the entire class is maintained, right? Now, so we've written the function of the salt bridge is to maintain the electrical neutrality. And as we discussed, just like in physics, you know that there is a point of entry of the current, there is a point of the exit of the current. So the circuit has to be complete. So if you notice over here, the circuit gets complete with the introduction of the salt bridge, and my galvanic cell or voltaic cell is able to work longer. It is not that this type of circuit will go on forever, right? It's not a perpetual motion machine, because what will happen is over time there will be accumulation of the charges, the ions will build up, but yes, it works longer compared to when you do not introduce a salt bridge. Now, coming to again the half cells. Zinc is getting converted into zinc ions, right? Okay, let me show it by, and first let me just organize it a bit more. Zinc is getting converted into zinc ions. So what do is I make it a little simpler, because I can't draw this diagram every time I have to represent a galvanic cell. So I made it a little simple. Zinc is changing into zinc ions. What is happening over here is loss of electrons, so there is oxidation happening here, right? In the right hand side, the copper ions on the other hand are getting converted into copper, right? So what do is I separate the ion and the metal by a single oblique line, by a single slash. Let me make it a little more expressive. So I've got zinc in the form of solid, a single line, zinc ions in the form of an aqueous solution. Copper ions again are in the form of an aqueous solution, and I have copper which is in the form of a solid, right? Here, what is the concentration of the zinc ions? Okay, let me come back to that later. What now is there is the two of them are connected by a salt bridge. So in order to represent the salt bridge, just like this U-tube, I have put two slash lines over here. If you notice, these are inclined, these are not straight. It's not by mistake, it's by rule. We draw them slightly inclined. The electrons are flowing from zinc to copper, right? So let me represent it by this. What does this become? This is the simplistic representation of a galvanic cell, and it is called as cell representation. In the cell representation, it's lone. You remember it by lone. Left hand side represents oxidation, and this is called as the anode. So here my zinc half of the cell becomes the anode. So automatically the copper half of the cell becomes the cathode, and I am representing it as reduction, and we are showing it on the right hand side. So if you remember load, you will be able to represent the right hand side very easily. One more point to be added over here. Now here I have simply written aqueous solution. As you advance in your study, you will realize that the concentrations of the solutions that we are taking in these beakers also makes a difference to the potential or the amount of potential that you are obtaining in a galvanic cell. I've introduced a new term over here, potential. I'll be talking about it next. Now, the concentration of the solution also affects the potential of this cell. So we need to represent that concentration as C1 and C2 for each of the two cells. Right? This whole setup is what we call as an example of an electrochemical cell, where chemical energy and electrical energy are being interchanged. This type of a cell where we are converting chemical energy to electrical energy is specifically called galvanic cell or voltaic cell. During your course of study, you also must have studied cells where you use electricity in order to break down a substance, right? And those are called as electrolytic cells. We shall be discussing that also in a separate video, but presently we will focus our attention on to galvanic cell or voltaic cell, right? And I am now going to move on to electrode potential. Now I am giving you a quiz question over here. It's actually very simple, and try to base the answer on the knowledge that you have acquired in your previous classes. So what I've done over here is I've changed the zinc rod to silver rod. So let's suppose we have a setup where we've got silver dipping in a solution of silver ions. So we've got silver in contact with silver ions in the form of silver nitrate solution. And we continued with the copper rod dipped in a solution of copper sulfate. Of course, our salt bridge remains the same. We are not going to touch on that. And we've got a galvanometer connected over here. Now, my question to you is, identify, first step, the anode and the cathode. Second, the direction of movement of electrons, the direction of conventional current. Yes, I am glad to see that some of you are able to answer the question. That means you got your fundamentals right from your previous classes. If not, don't worry, we are going to cover them slowly, step by step, and this is the easiest topic. Believe me, the easiest topic that you can find. So anode and cathode, direction of electrons, direction of conventional current, okay, and the last thing that you're going to do for me is to represent this cell. So you have to show me the cell representation. Try answering these questions based on, you know what you're going to base your answer on? What you have done in your last year is the activity series of metals. I love to take these two examples because these relate to the knowledge, or they connect to the knowledge that you have already acquired in your previous classes. So the classical example that I take is the zinc copper combination and the silver copper combination. So that makes it easier for the students also to understand the concept. So based on your activity series of metals, yes, you are right. Potassium, sodium, calcium, magnesium, aluminium, zinc, iron. Remember this series? Potassium, sodium, calcium, magnesium, aluminium, zinc, iron, lead, copper, hydrogen. Yes, go on, very good. Now compare silver and copper. Also you know which of the two is more reactive, which of the two will have more tendency to go into the solution as ions. Sorry, I've thrown a hint over there. Now you should be able to get it. Yes, absolutely right. When the two of them get connected, now here what happens is copper takes up a different role. It says when I am connected to silver, it's like, in the presence of zinc, zinc was more powerful than copper. But if I have silver nitrate and I add copper to its solution, what will be the reaction that will take place over here? Perfect. It will give us copper, nitrate, and silver will be separated out, right? So the same thing happens over here. So copper is turning to copper ions. Perfect. So Cu changing to Cu2 positive plus 2 electrons. Then what about silver? Yes, Ag positive on the other hand gaining electrons in order to turn to silver. So earlier we had a zinc copper galvanic cell. Now in the case of silver copper galvanic cell, what will be the anode? Where is oxidation taking place? Yes, in the copper half cell. Where is reduction taking place? Silver half cell. Perfect. What will be the direction of flow of electrons from copper to silver? Very good. Direction of current? Super. Silver to copper. So impressed. Cell representation. Now where is oxidation taking place? Lone. L-O-A-N. Left hand side I will write copper as a oxidation reaction. So my concentration is C1. We can omit it out at present and just write aqueous here. Correct? And for copper it is solid. So Cu solid in combination with copper ions, salt bridge, silver ions in aqueous solution in combination with silver solid. And what else? There's one more thing that we have to show. Perfect. The direction of flow of electrons. So this becomes my copper silver galvanic cell. So this way we can have a number of combinations of galvanic cell or voltaic cell. Now the question arises, how do we know? Okay, one hint that I have given you here is the activity series of metals. Now that activity series of metals doesn't cover all your metals, and moreover it doesn't cover non-metals as well. You can have galvanic cells involving non-metallic combinations as well, right? So how do we gauge what is going to be the anode and what is going to be the cathode? For that we are going to talk about electrode potential. Before I go on to electrode potential, let me introduce something interesting over here. Now, we've connected a galvanometer. Galvanometer is a device which is going to give us the direction of the current. Can you tell me in which direction the galvanometer needle will deflect? Very good. Yes, I know you can see the answer over there. Direction of current is from silver to copper. Now, instead of connecting a galvanometer, what if I connect a voltmeter over here? A voltmeter is a device which will give us the difference in potential in the two half cells that we are using in this particular voltaic cell. And how do we, so this V, the value of V over here, potential, is what we call as potential difference between the two half cells. Our next video will be based on electrode potential and standard hydrogen electrode. So stay in touch, stay subscribed, stay happy and healthy. Happy studying to all of you.